Hello, everyone, and welcome to another lesson. Professor Mab here. The topic of today's lesson is phase change processes and thermodynamic property tables. There are many practical situations where two phases of a pure substance coexist in equilibrium. Water exists as a mixture of liquid and solid, or as a mixture of liquid and vapor in many industrial applications. Here, we use water as a familiar substance to explain the phase change processes. Other pure substances exhibit the same general behavior. Let's consider a cylinder piston system containing water in a way that the system is designed so the piston will maintain the pressure constant at 1 atmosphere. By changing the temperature, the phase of water will change. Let's start by state 1, where water is at room temperature of 25 degrees Celsius exists in the liquid phase called a compressed liquid, defined as it is not about to vaporize. Heat is now transferred to water, but its phase does not change until its temperature rises to 100 degrees Celsius. Its volume increases slightly, as we can see that at state 2 on temperature volume graph. At this point, water is still a liquid, but any heat addition will cause some of the liquid to vaporize. A liquid that is about to vaporize is called a saturated liquid. Once boiling starts, the temperature will remain constant during the entire phase change process, and it only rises after the liquid is completely vaporized. Along the vaporization line, at any point, such as point 3, the cylinder contains saturated liquid-vapor mixture. Along this line, as heat transferred to water continues, the amount of vapor increases and its volume expands. The vaporization continues until the last drop of liquid is vaporized, and we arrive at the state 4. At this point, the entire cylinder is filled with vapor that is on the borderline of the liquid phase. Any heat loss from this vapor will cause some of the vapor to condense and change to liquid. A vapor that is about to condense is called a saturated vapor. Once the vaporization process is completed, water only exists in vapor phase. Any additional heat transfer results in an increase in both the temperature and the specific volume. For example, at a state 5, the temperature of the vapor is 200 degrees Celsius. At this state, if we reverse the process and transfer some heat from the vapor, the temperature will drop, but no condensation will occur. A vapor that is not about to condense is called a superheated vapor. If you say that water boils at 100 degrees Celsius, it is technically incorrect. The correct statement is water boils at 100 degrees Celsius at 1 atmospheric pressure. If the pressure inside the cylinder were raised to 475 kilopascals, water would start boiling at 150 degrees Celsius. This is called the saturation temperature, which is the temperature at which a pure substance changes phase at a given pressure. Similarly, the saturation pressure is the pressure at which a pure substance changes phase at a given temperature. Thermodynamic tables are available for all substances that list the saturation temperature against the pressure or the saturation pressure against the temperature. We explained the phase change process for water on temperature volume diagram at 1 atmospheric pressure. Now we discuss the same process at different pressures as shown in this graph. As you can see, at higher pressures, the vaporization process occurs at higher temperatures. Also, the specific volume of the saturated liquid is larger, and the specific volume of the saturated vapor is smaller at higher pressure. This results in shorter horizontal lines representing vaporization process. As the pressure is increased further, the saturation line continues to shrink, and it becomes a point. This point is called the critical point. It is defined as the point at which the saturated liquid and saturated vapor states are identical. For water, the critical point occurs at 22.06 megapascals and 373.95 degrees Celsius. If we look at the left side of a TV graph and connect the saturated liquid points at different pressures by a line, this line separates the compressed liquid region from saturated liquid vapor region. This is called the saturated liquid line. Similarly, we can connect the saturated vapor points by another line, called the saturated vapor line, separating the saturated liquid vapor region from superheated vapor region. These two lines meet at the critical point, forming a dome called the saturation dome. All the compressed liquid states are located to the left of the dome. All the superheated vapor states are located to the right of the dome, and the saturated liquid vapor mixture region, which is also called the wet region, is located under the dome. For most substances, the relationships among thermodynamic properties are too complex to be expressed by simple equations. Therefore, properties are frequently presented in the form of tables. Some thermodynamic properties, such as temperature and pressure, can be measured easily, but others cannot, including internal energy, enthalpy, and entropy. These properties are calculated by using the relations between them and measurable properties. The results of these measurements and calculations are presented in thermodynamic property tables. A small part of a property table for water in saturated liquid vapor region is shown here. For other regions, separate tables are available. In this table, you can see different variables and their SI units in the top row. From left to right, we have temperature, pressure, specific volume, internal energy, enthalpy, and entropy. In the saturated liquid vapor region, the subscript F indicates the properties of a saturated liquid, and the subscript Eg indicates the properties of saturated vapor. Additionally, subscript FFG indicates the difference between the saturated vapor and saturated liquid values of the same property. Algebraically, it can be written as YFG equals YG minus YF, while Y could be any of the following variables: specific volume, internal energy, enthalpy, or entropy. Later in this lesson, we'll learn how to use property tables effectively in several examples. An important thermodynamic property that is used to characterize the saturated liquid vapor mixture is quality, or X. It is defined as the ratio of the mass of vapor to the total mass of the mixture, with total mass being the sum of the liquid and vapor masses. It has a value between 0 and 1. The extreme values of 0 and 1 correspond to the two ends of the saturated mixture: 0 for saturated liquid and 1 for saturated vapor. In order to relate the quality to other mixtures' properties, we consider a saturated mixture as a combination of two subsystems, the saturated liquid and the saturated vapor. So the properties of this mixture will simply be the average properties of its components. For example, the total volume of the mixture, V, is the sum of the volume of a saturated liquid and the volume of saturated vapor. Using the relationship between volume and mass, we can bring in mass into our main equation. Eliminating MF results in the following. Now, if we divide this equation by M, we get this new relationship from which we can calculate the mixture's quality using thermodynamic properties of the mixture. As discussed before, several thermodynamic properties exhibit the same trend in liquid-vapor mixture region. These include a specific volume, internal energy, enthalpy, and entropy. Therefore, we can write similar relationship between them and the mixture's quality. So we have these equations for specific volume, internal energy, enthalpy, and entropy. We now summarize what we learned about various phase change regions on a TV diagram. As mentioned before, this discussion is also valid for several other thermodynamic properties, namely YY, while Y could be a specific volume, internal energy, enthalpy, or entropy. Under the saturation dome, we have the saturated liquid-vapor mixture region. This region is characterized by saturation temperature, saturation pressure, or a thermodynamic property having a value between its corresponding liquid and vapor values. The superheated vapor region is located on the right of the dome. It is described by lower pressure than saturation pressure, higher temperature than saturation temperature, or higher thermodynamic properties than vapor values. The compressed liquid region is located on the left of the dome. It is characterized by higher pressure than saturation pressure, lower temperature than saturation temperature, or lower thermodynamic properties than liquid values. Note that while saturated and superheated tables are widely available, compressed liquid tables are not as commonly available. One reason for the lack of compressed liquid data is the relative independence of compressed liquid properties from pressure. In the absence of compressed liquid data, a general approximation is to treat compressed liquid as saturated liquid at the given temperature. This is because the compressed liquid properties depend on temperature much more strongly than they do on pressure. This video, please let me know your questions in the comments section.